important. It's central in ecology. It's called the intermediate disturbance hypothesis, which will be a big part of this segment of our class that we're in. But we're also going to talk about succession, which comes in two forms, primary and secondary succession, which is essentially your response to disturbance. And then the last thing we're going to talk about is, well, how does disturbance and succession and all of these factors, how does it relate to biodiversity? And mostly we're going to be focusing on species richness. So for this next part, I need 2 volunteers, by the way. I need 2 volunteers to come up on stage. Jack and, somebody else. Sully, beautiful, come on up. While they're coming up, just so you have your feet on the ground with what we're talking about, we're now in sentence 3 of the 5-sentence narrative for this class. We've talked a lot about all of the systems that exist across our planet and change over space and time, and we've talked about a little bit of the ecological background. I'm going to give both of these guys a copy of the entire narrative, but so you can see we're right in the middle of number 3. So somebody who has a phone that's readily available, can you do me a favor? And you're going to time both of these guys reading the narrative. So first is it's fine. You'll be all right. It won't matter. You're going to just read it loud and proud. It doesn't matter how long it takes you just reading through the entire thing. Can you just time? Sully's going to go first, and then we'll do Jack next. So when you're ready, he'll start when you start.
Everything on Earth is highly interconnected with numerous natural systems that vary over space and time. Living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems. Technology and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development of sustainable solutions.
And stop. Beautifully done. The only thing better than the reading of that is whoever wrote that. It's fabulous stuff. Give Sully a hand. Sully, don't go away yet. We're going to continue on here. So Sully just read through this. Now, you have the time. I'm going to have Jack read through it as well. Jack, you're next. Keep it. We're going to do more here. All right, this is the second time. You're going to get a little tired of the narrative, but if I figured we're going to repeat something a couple times, we might as well do the narrative. So Jack, you're up this time. All right. Ready? Garrett, you ready? Good. All right, go.
Everything on Earth is highly interconnected with numerous natural systems that vary over space and time. Living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems. Technology and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development of sustainable solutions.
Beautiful. Give Jack a hand as well. All right, we have a little bit more to do on this. So I know you're going to get a little tired. Okay, we're going to simulate something. So Sully, you're going to go again, and we're just going to do a little comparative analysis. And because we're scientists, it's always fun to quantify things. So the time that you did for the reading the first time is the baseline. Under normal circumstances, Sully, totally uninhibited by any type of disruption, is just able to read that in how much time? 43, that's great, right on. 43 seconds. All right, so now we're going to have Sully, we're going to change the treatment type, just do a little experimental trial. We're going to have him read it again, all right, Sully? All you got to do is read it, okay? Ready? All right, same thing.
Everything on Earth is highly interconnected with numerous natural systems. I can't see it. That vary over space and time. Living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural technology, population growth has enabled humans to increase the rate and scale of their environmental impact.
disruption. Thank you, Sola. You can take your seat. So we added a little disruption. We changed it. How would you describe that experience, Soli? Were you able? What did you have to do? Was it easy to read the second time?
No.
All right. Cool. We're going to come back to that in a second. All right. Now we got Jack. We're going to let Jack go ahead here. How much was Jack's baseline? We have two different readers. We don't want to compare Soli to Jack. That's messing things up. So we're just doing treatment types. What was Jack's on again? 4132. 4132. All right. We're ready to go. Go ahead, Jack.
Everything on Earth is highly interconnected with numerous natural...
Get back.
Bullying. With numerous natural systems that vary over space and time, living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems. Technology and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development of sustainable solutions.
Stop. What do we got? 42. Oh, very nice. We were about a delta of 1 second each. Give Jack a round of applause. All right. So, stay with me on the analogy here, because I'm trying to demonstrate something. Disruption, so I was disrupting your ability to have focused attention on that, but disruption is anything that causes an influence to the way things that normally would go. So you have a normal processes taking place, in this case reading, and ecology, it's productivity of the ecosystem going on. Disruption is going to be anything that comes into that. There are two key definitions that are very important, and when I use this language, or Mr. Hobby uses this language, or you encounter it in literature or on tests, you should understand what it means. So here I've just given you a little bit of information, but when we're talking about a disturbance, we're talking about a change in the environment. I disturb both of them. Agree or disagree? Agree, right? Mm-hmm. So let's look at this. So when we're talking about disturbance, it could be anything. It could be a physical, some type of an event that causes chemical or physical change or biological agents being changed, and it's going to affect mostly the biodiversity. On that first slide, the intro thing, I said biodiversity, higher is always better. So we're going to measure what the impact of the change is by looking at the impact on biodiversity. Here's where the distinction comes. So I was disrupting Soli, and it kind of slowed down his ability to continue on the process, which was reading. But in an ecological sense, that would be the ability for the ecosystem to continue on and increase over time in productivity. But he resisted it, right? He tried to block it out. He tried to tune his focus in and continue to read in a disciplined manner because he knew that was a task. The ecosystems tried to do the same. So when we talk about what is the level of resistance in an ecosystem, this is what we're talking about. How well do they push back against the forces of disruption? Now, when I disrupted Jack, it was a little bit different. I just took the narrative out of his hand and threw it on the ground. It was a single event, and he had to go get the narrative, pick it back up, and resume the reading. So he was still trying to keep on being productive in the process of reading. Ecosystems try to continue in the same way, but how long it takes for them to respond, which is for Jack was about 3 seconds, but then he sped up his reading, so it ended up only being a delta of 1 second. A little error in our experiment, no big deal. But that is called resilience. Do not use these as synonyms. They are not synonyms. The distinction matters. All right. Now we want to talk about this theory that I stated at the beginning of the lecture, which is a very central theory in ecology called the intermediate disturbance hypothesis. The first time that you think about disruption, or try to imagine what disruption is in your head, and if I tell you it causes a change in the biodiversity of an ecosystem, your instincts are to say that that is really bad. But ecosystems at their most productive state, competition has been tipped. The species that have the most competitive advantage, like something that can shade out a whole area like a tree, is going to start to become the dominant species in an If one or two or three species start to become dominant in the ecosystem, what happens is the biodiversity is low. They've outcompeted everything else. So on this side, let me just break down this graph here now. This shows the intermediate disturbance hypothesis, and it has this curve, and it says species richness, but you could also just kind of think of this as biodiversity. When disturbance is very low, and the ecosystem is at one static state for a very long time, then you have competition is also low because a few species have already outcompeted everything else. So the biodiversity is low. If you have a lot of disturbance that's extremely frequent and it can be really harsh, it can be very severe, then the biodiversity also goes down. It's too much disruption. Every time you start to get productive, another tornado or hurricane comes in and wipes everything out. The productivity ends up being low, so competition over here is high, or is also sometimes low because there's just not enough organisms that can withstand the disturbance. An ecosystem at its healthiest state is somewhere in the middle, which is represented by this bell curve. So what that tells us is, in standard ecosystems, there's a certain level of disruption that is necessary to maintain the overall health of the ecosystem. But as soon as you have too frequent or too severe, the biodiversity plummets, and the opposite is also true. If you never have any disruption, the biodiversity is also low. This example from the textbook, I'll just show you because I thought it was a pretty good example. What they're trying to show you is the species richness of algae, so they're just measuring the primary producers of algae in an aquatic ecosystem. Well, when there's not very much disturbance, they're very low because the most dominant species outcompete everything else. These snails represent a disturbance because they consume the algae. Once you have the snail's presence there, what happens is if there's too few snails, the dominant species reign. When there's an intermediate level of snails, it helps balance out things, and so the species richness and biodiversity is the highest. But if you have too many snails, they're over-consuming, and the biodiversity is low again, and the only species that are surviving are maybe the ones of lowest preference of the snails. So they're out-competing all the other species because they're able to withstand the disturbance the most. Intermediate disturbance hypothesis. This will come up a number of times during this unit. All right. Oops, here we go. So now we're gonna go in a slightly different direction, but kind of build from there, and we're gonna talk about this thing called succession. And I had brought something that I wanted to share with the class, and only because it was something that occurred, it was really important to me. When I was in graduate school, I worked at the Roe Bird Sanctuary in Nebraska, where one of the largest migratory phenomena on planet Earth occur, and that's the migration of sandhill cranes. Millions of cranes come through this really narrow area right in the central part of Nebraska, and they nest for about a month's time between Grand Island and Kearney, Nebraska, and they stay right there, and then it's like an hourglass. They come from all over, and they all stay there, and then they go back out, and it's a really beautiful thing. When they wake up in the morning, there's so many cranes that it blocks out the sun when they take off to go feeding. It's an incredible thing. And the Roe Bird Sanctuary does a lot of work to study cranes and other songbirds that migrate during this period of time, and I was working there part-time. But people come from all over the world to see this phenomenon, not just bird watchers. While I was working there, Jane Goodall, does anyone know who Jane Goodall is? Everybody should hopefully know. She's very famous. And she had done a lot of studies in Africa and helped us understand the intelligence of animals and helped us understand the intelligence of human populations and societies over time. She's a prolific author and lecturer. But she came to visit, and she gave me this book, and I have a signed copy of this book from when I met Jane Goodall in 2001. And she just has her name right here. And this quote isn't from a quote that you can find on the internet. It's a quote from my book. And it was an answer to a question that I asked her. I said, well, with the disruption that's occurring in the environments all over the world, I was studying snakes at the time, trying to do research on snakes, figure out if disruption was causing these snakes to go extinct in Nebraska. And what are we going to do about all of this disruption and mass extinction and that? And she said that there's that nature is unbelievably resilient, and that there's always reason for hope, which is the title of the book. And I only wanted to bring that up because resilience is what we're talking about right now, and succession in response to disturbance is something that's key. This was a single moment in my life that only lasted about 5 seconds. It was a short exchange, and it was kind of a life-changing thing. And my advice is never miss an opportunity to be inspired by something or someone. So I wanted to bring that quote out before we get into succession here. Succession, though, as a definition that I've given you, is the predictable replacement of species over time. And what's occurring is, just like what we saw on this previous slide about biodiversity, certain species will replace others because of competition or in response to disturbance. So this has to do, what is this? Did I skip this? Oh, we'll come back to it. It's okay. We'll come back to it. We'll do it at the end. Succession is the response to disturbance. There are 2 types of succession, and we're going to talk about both of them right here. Primary succession is what takes place when you have a very severe disruption that takes the environment all the way back to the abiotic factors, basically only. It's bare soil, totally exposed, bare soil or rock. So when we look at examples of ecosystem disruption, if you see the ecosystem being rolled all the way back from what it used to look like to bare soil or rock, then the replacement of species that come back in to repopulate that ecosystem over time is always going to be primary succession. Another key definition that comes up a lot is the types of species that exist at different parts along this timeline continuum. Pioneer species are the first ones to come back and colonize an area. And climax species are the ones that are usually K-selected species that will remain unchanged for a great amount of time if there's no disruption to the ecosystem. So if we have not enough disruption on the intermediate disturbance hypothesis and the biodiversity is low, it's because we're here. If the disturbance has just occurred and it was really severe, it's because we're here. So if we apply the intermediate disturbance hypothesis to this picture, can someone give me an answer for the area that they think is the most biodiverse? There's names there. Campbell?
Rainforest.
That's an example of an ecosystem. Use this picture. That's good. I like that, but Sloan?
Perennial wildflowers and grasses.
It's probably somewhere in this perennial wildflowers and grasslands. So even though that area doesn't look like it may be very biodiverse, there's all sorts of species there, and they're very evenly distributed. So it's probably somewhere in here between this and the shrubs, maybe getting into this. It's in this middle area. This is the most biodiverse, and the 2 edges on the end are the least biodiverse. Secondary succession looks very similar. This is what succession that proceeds after a disruption occurs, but the disruption is not as severe. It only takes you back maybe a few steps on this continuum of an ecosystem, not all the way back to bare rock or earth. And so what we're talking about is there's some evidence usually of primary producers, and their grasses, wildflowers, these sorts of things, could be lichens or other organisms, and then succession proceeds from there. I wanted to make sure to pause here because this is a common misconception that I've seen a lot with students, and it's the idea that after a disruption occurs, first primary, then secondary. I didn't come up with these names, and I realize they're misleading, so this is your opportunity to realize this misconception now. It doesn't go primary and then secondary. It is either primary or secondary. If it goes all the way back to rock, the succession that occurs is primary. If it just takes it back a few steps or down on the primary producer scale, then it's secondary succession. Does this make sense so far? Just doing a little math. What's the time at? You go, oh, beautiful. We're rolling. I'm going to go back and I'm going to stop here and we're going to do this quick case study that I accidentally skipped by and I got excited about my book. So we're going to do this. People have probably heard in the news already about the California wildfire, which is the most damaging. It's not the largest wildfire that's occurred in California history, but it's the most damaging in terms of economic damage, and I think it's the most acreage, but not necessarily the most. It depends on what measurement you want to use, but it's been very severe. It's been in the news. Over 1,000 people were missing. Thousands and thousands of people were displaced. 60 people, or I think actually over 70 people, unfortunately died. What hasn't been talked about as much, but obviously matters, is there's also this is an example of a disruption and its cause effect to the ecosystem as well. So I just want to show this video in case you haven't seen that much. The focus is more on these neighborhoods, but you can see the ecosystem in the background. And I want you to think about and try to pin some answers to these questions. Rating the resistance and the resilience based on your observational skills. So don't just write kind of general stuff. Based on what you see, providing examples of what the resistance and resilience of this ecosystem is. Identifying changes, physical changes that have occurred, and then the last is how do the changes from this should say number 2, I'm sorry, impact the forest ecosystem. So we're going to take a couple minutes here, and my least favorite thing about lecturing with people is when I say take a couple minutes to answer these questions, and then you don't do it, and then you do poorly on the test. I've already said that a million times, but I'll keep saying it because you keep doing the same behavior, so it's all good. Let me get this going here, sorry. Here we go. Couple minutes. Sound isn't working, sorry. Tragic way, it's almost better with no sound. We played this again, but I didn't hear much writing, but let's just turn and talk really quick and focus on number 2. What are some of the physical changes that you noticed based on this? Go ahead. Turn and talk. Everybody should be talking.
You can say all the houses are
What's interesting, I just heard on the radio 2 days ago, everything waiting to let people in that
kind of like a tree, something is just destroyed.
We were dead and hollowed out and they're starting to fall down. One person, unfortunately, went back to see how their house was doing. And
2 physical changes.
2 days after the fire was already contained in that area. The trees, some of them you see that look like they're standing, are for the most part, probably also dead.
Identify 2 physical changes that occur in the forest ecosystem when a mature tree dies. It falls over. How is this caused by a fire? It's about 2 physical changes that occur in the forest ecosystem.
should be quite a bit of diversity of answers. I did this exercise, and I thought of 16 things that I could think of for number 2. What are some of the physical changes that you observed that occurred in this ecosystem? Give me some stuff. Yeah.
Wait, in this ecosystem or
in this one?
Oh.
In this example.
Well, the houses were leveled and crumbled all around, so I guess stuff that would prevent plants from growing in certain areas.
Oh, good. I was going to say that is true, and while the human tragedy is bad, it also doesn't matter, but I really like the way you ended it. So the rubble and the parts of the building are down on the ground, and that can potentially prevent plants from growing in the future. Yeah?
The overall density of the forest.
The density of the forest is down, but tell me about the physical change. Density, I like that, but give me a little bit more.
Like, I guess the
density of what? Like, what physical thing do you see being less dense? Because there's, amazingly, most of the matter that existed is still there, but it's been transformed. So what part is less dense? So we've transformed what into ash? Trees, right? Give me a couple more things. Yeah.
The tree canopy was destroyed.
Tree canopy was destroyed. So somebody else answered number 3 based on that answer. Why does the change in the tree canopy, why would that have any influence? Jack?
Because then there's more sunlight.
More sunlight. And what do we know about access to sunlight? Is that a good thing? For some things.
I'm going to say, like, with less mature trees, the saplings won't drop the same, so then there'll be less, like, occurrence of young trees in the future.
So there was an answer about with less mature trees, there's fewer seed dispersal, maybe fewer saplings. I like that. Maybe give me 2 more things. Sully? So animals that love to live in the place where you would expect to find them, where they would reside, their niche, as it were, is destroyed, so they have no habitat anymore.
well, now since all the mature trees are gone, it leaves room for like new species to grow.
New species can grow because some of the dominant ones have been taken out. Somebody give me something about biogeochemical cycles, because that is definitely something that's been altered. How do you think biogeochemical cycles have changed? And specifically, which ones? Yeah.
Well, the carbon cycle, with all the burnt trees, there'd be a lot more carbon in the ground and everything.
There's carbon in, actually when the trees burn and they're combusted, most of that goes into the atmosphere. The carbon that used to be sequestered as part of the sugar of the trees is in the atmosphere, so we've changed it in that way. What about photosynthesis? It's way down. Tell me about the nitrogen cycle. How would the nitrogen cycle be altered? It would probably also go down because of which critical thing that's part of that cycling.
Trees.
No trees, no plants, no assimilation, not moving in and through different biotic things. What about phosphorus? Anything change there? Or water cycle? You think the amount of runoff looks different with no trees? The amount of infiltration? Of course, all of these things have been changed and have been impacted. Let's scan through here on succession again really quick. We got to click back. We get through here, back to where we were. So when we consider the succession process, so after this disruption has occurred, the one that I just showed, which was the forest fire, that ecosystem will recover over time, and that's something that's normal. And the rate that succession will occur, whether it's this disruption or any disruption, will be dependent on a few key factors. So one of them is latitude. We talked about this a bunch of different times. We said the composition of biomes is primarily based on where they're at latitude. So latitude is very important for access to sun. It drives the convection cycle, which tells us access to precipitation. All of those things, if you have abundant sun and abundant precipitation, it'll increase the biodiversity and biomass. So latitude has a lot to do with it. I just wanted to give a shout out to Campbell because his answer earlier about succession, he said in the rainforest. Disruption in the rainforest is not as big of a deal because a productive ecosystem to begin with. The speed of succession also is dependent on time, and by time I don't mean how much time has gone by since, how long does it take for this specific succession, but it means what did the ecosystem look like before the disruption? How much time was it between the last disruption and this disruption? Was it at a very mature state, or was it somewhere in the middle? Whenever you have a disruption, it's going to knock you back on that time, this little continuum here. So this time, it's going to knock you back a few steps. So if you're only here and you get knocked back a few steps, you're further back than if you were here and got knocked back a few steps. So disruption, the rate of new species overtaking one another, and that successive process is dependent on the frequency or the interval between disruptions. The habitat size matters a lot. If the habitat is larger, that is generally better. It increases the resistance and the resilience both. And if you have a disruption that knocks it back, the resilience more critically is going to be the thing that is influenced, that's beneficial. It will come back quicker. There's a greater number of species opportunity potential. Also, the distance from other communities, which is something that we'll spend most of our time talking about in our day tomorrow and this group tomorrow. So I'm just going to kind of leave that one out there. But the distance you are away, that matters because the species that come back in to repopulate the ecosystem are going to come from neighboring ecosystems. I have one more case study. Check that out. Disruption, am I right? I have one more quick case study that I want to do here. And this is kind of a quintessential case study. So we're going to watch this together. It's about a 5-minute video, and I want you, this reminds me a lot of something that would be, it's a video version of an FRQ that you might see on an AP exam, or you might see on one of our tests where we're asking you to do a bunch of different things and parts based on one case. So this is Mount St. Helens, which erupted about the time that I was born. So the succession that you're seeing, just as interesting anecdote, is about the span of what my lifetime is. So I'm going to ask you to do these 5 things. Rate the severity of disturbance, thinking about the impact of that disturbance after the disturbance happened. What type of disturbance was this? Or what type of succession occurred, I mean. Number 4, looking at pioneer species. And number 5, identifying some climax species. Here we go. I hope the audio plays for this. Okay, give me 1 second here. It's decidedly worse if you can't hear it. Let's see about this. Oh, look, it's back. Now that song, by the way, outstanding song. Let me go back to this. Okay, here we go. Perfect.
Mount St. Helens in Washington State is one of the most well-monitored volcanoes on the planet, and with good reason. It is still active, and more than 3 decades to the day after it launched a stunning and destructive display of lava and ash, it continues to transform a region and its ecology. Even now, scientists are still learning about the aftermath and how some life is emerging from the ashes. Science correspondent Miles O'Brien has the story, part of our new weekly series about exploring the leading edge of science.
36 years after its spectacular, deadly eruption, Mount St. Helens still rumbles and bears scars from that earth-shattering day. But hike down the slopes, away from the jagged crater just a little, and you'll see Mother Nature hard at work. And there's a good chance you'll bump into a team of scientists led by John Bishop. He is an evolutionary biologist at Washington State University, Vancouver.
The goal of our research is to understand how plant and animal communities reform after a catastrophic disturbance.
Bishop is one of a select group of researchers studying this rebound from a volcanic eruption. Back in 1980, Mount St. Helens had given scientists all kinds of clues that a big disturbance was brewing. 2 months before it blew, the volcano was venting huge amounts of steam, and there was a series of earthquakes. Even with all those ominous signs, the eruption was larger than anyone predicted. It happened at 8:32 on the morning of May 18, 1980. An earthquake caused the north face of the mountain to collapse.
After that, it uncorked an explosion that was directed horizontally and leveled the forest to 13 miles out from the volcano.
The eruption column of volcanic ash and gas rose 80,000 feet, while a tsunami of 1,800 degree gas and rock raced down the valley at 450 miles an hour, a so-called pyroclastic flow.
Anything biological that was remaining after the landslide would have been completely vaporized. It was just a barren landscape, gray and pumice-colored.
It killed every living thing in a 230 square mile area. What was left was akin to a moonscape. 57 people died. Some remains were never recovered. Bishop and his team have had a front row seat as nature got busy bringing this place back to life. They wanted to know where it begins and how it takes root. Here, it started with these purple flowers. Alpine lupin were the first plants to return. For many years, they were pretty much the only game in town. But as they went through their life cycles over several seasons, they created soil from the volcanic ash. And that made it possible for woody plants, like the Sitka willow, to find a home. They are how a forest gets started. But it hasn't been easy for them.
One of the things we've realized about these willows is that they're not getting big. That's important because they create habitat for birds and mammals. We've learned that these landscapes are characterized by extreme instability in the populations of the plants and animals that colonize them.
In a recovering ecosystem like this one, where just a few species have managed to regain a toehold, even seemingly insignificant pests can play an outsized role in how the landscape bounces back. These weevils are an invasive species with a particular taste for the Sitka willow.
Any stem larger than about 1 centimeter is usually destroyed by this weevil. And the effect of it is to keep these plants small, not let them form the architecture that's needed for bird and mammal habitat.
But Bishop says it's important to remember we're still early on in what will be a very long game. He says the plants and insects will battle it out over time, and eventually the ecosystem will become more diverse, more stable, and this will be a forest again.
When I'm out there working on Pumice Plain, one moment I'll look around and I'll be stunned by the amount of vegetation and the number of birds that are present. But the next moment I step back and think, there is hardly anything here. We're set game.
He says the number of birds, more sticky.
This is a great picture, by the way. So in the area where the disturbance was the most severe, you see it's taking the longest time for it to recover. The further out you get, the more succession has already taken place. Good examples of how succession, species coming back and reestablishing leads to more succession. All right, gang. More soon. Have a fantastic Wednesday. Thank you.
Mr. Abbott, do you think for Quinn's birthday we could play in the sandbox tomorrow?
Quinn's birthday?
Birthday today, but we got a lecture.
We'll see. See if we can work it in.
I'd like you to get the data from somebody and then use it to have the lectures match.
Is it like one of those quiz things that you turn in and sit down?
Maybe, yes. I'll be out.
Cool. Alright, everyone. Alright, I'll talk to you Wednesday. Cool. I'm going.
Okay, cool. Thank you, Mr. Taylor.
Thank you, John. Have a great day.